Hello and welcome. Thank you for joining us for this Nuclear Innovation Alliance event in support of the publication of the new NIA report, Right-Sizing Reactors, Balancing Trade-offs Between Economies of Scale and Volume, written by Dr. Jessica Lovering. If you would like to read the report, I invite you to download it now from the NIA website at www.nuclearinnovationalliance.org. My name is Ben Finzel. I'm president of Renew PR. I have the pleasure and privilege of serving as NIA's communications consultant, and I'll be the moderator for today's conversation. One of the NIA's principal activities is serving as an information resource for understanding the challenges and opportunities related to new nuclear development and deployment. So, as we consider policies, regulations, and financial and technical support needed to develop and deploy a new generation of nuclear reactors, how should we view the question of what size these reactors should be? This report provides background, analysis, and recommendations for considering that question. Shortly, we'll hear from the report author, NIA Senior Fellow, Dr. Jessica Lovering, who will highlight what's in this report and how it might be used. From there, we'll have a roundtable of industry experts who can speak to different size requirements and opportunities. This panel will include Rob Stewart of Alba Energy, Rita Baranmal of Radiant Nuclear, and Per Peterson of Kairos Power. But first, we'll hear from NIA President and CEO Judy Greenwald. Judy's going to introduce NIA and talk about the impetus for the report they are publishing today. Judy.
Thanks so much, Ben, and welcome everyone. For those of you who don't know us, NIA is a think and do tank whose mission is to help create the conditions for success for new nuclear energy so it can play a major role as an energy security and climate solution. Recent events in the nuclear energy sector motivated this report. For several years, there has been growing excitement about a new generation of mostly smaller reactors. Then Vogtle 3 and 4 came online, which are advanced reactors with new inherent safety features, but they're similar to more traditional technology in that they're large light water reactors. Also, demand forecasts are being revised dramatically upward. These two developments are renewing interest in large reactors. This has raised questions about whether reactors should be large or small. There are trade-offs between large and small size reactors, for example, in terms of speed of innovation cycles, financing costs, project management challenges, and economies of scale versus economies of multiples from factory fabrication. Different industrial and utility customers have different needs for power, high temperature heat, or both, and different reactor technologies have different design advantages. Policymakers, investors, reactor developers, customers, and stakeholders are making decisions now about what reactors to encourage and invest in. So that's why we dug into this and are here to share our insights. So thanks for joining us, and back to you, Ben.
Thank you, Judy. Before we get into today's program, I want to share a bit more about today's run of show. So after Dr. Lovering's review of the report, we're going to hear from our roundtable of experts representing leading nuclear developers, as I mentioned, and that discussion will be followed by a couple directed questions and then an open Q&A. You are welcome to put your questions in the Q&A box now if you'd like, and I will do my best to answer them in the order in which they're received once we start the Q&A a bit later in this event. And when you put your question in, please be sure to list your name and your affiliation as well. That's always really helpful. Now, let's turn things over to Dr. Jessica Lovering to talk about the report. Jessica.
Hey, thanks, Ben. Thanks, Judy, for the introduction. So I became really interested in this topic and this debate over size and economies of scale in my PhD research when I was looking at microreactors, and that's reactors that are smaller than, say, 10 megawatts electric. And I was looking at them for off-grid and microgrid applications. But when I was looking at cost and potential cost estimates for this technology, I kept seeing a lot of people estimate first-of-a-kind costs using this in a traditional engineering scaling equation where you just took the cost of a large-scale light water reactor like an AP1000 and kind of scaled it down or scaled it up to a microreactor. And you would get these kind of crazy numbers like $100,000 per kilowatt that would make it really impractical to ever build a microreactor or make it never be competitive, even for off-grid applications. And then when the NuScale project was canceled in Idaho, I started, reading a lot and seeing a lot of energy and nuclear advocates, both anti-nuclear advocates and pro-nuclear advocates saying this just shows that SMRs are really never going to be economically competitive because of economies of scale. And I just thought that this argument was a little bit oversimplified because, we expect that, yes, there's going to be economies of scale or diseconomies of scale for small reactors. But of course, the whole point of small modular reactors is that you would benefit from factory fabrication and modularity. So where was that trade-off and where was that point? So I wanted to, in this report, dig into really the economics literature and the data, both on economies of scale, but also economies of volume, modularity, factory fabrication. And so that's what we did in the report. And there's a lot of it, both from the nuclear history and also from a lot of other energy technologies and engineering studies. And this is a very concise summary of what we found. But big picture is that, yes, there are economies of scale for nuclear reactors, for the historical nuclear fleet. And what that means is that as you build nuclear bigger, the cost per kilowatt comes down, all else being equal. Of course, not all else is equal. So the other thing that happens as you build bigger is projects get more complex. You tend to have more cost overruns. As you build more, you get cost escalation. Projects take a lot longer to build. You get this thing called negative learning. And a lot of challenges with these large projects. What Bent Flodbjerg, this Danish geographer who studied a lot of mega projects, one thing he warns about is eternal beginner syndrome and the challenges with these big projects. And so there's a lot of other downsides for large projects too, even though we do definitely see real economies of scale for large nuclear. And then what we also see in the economics literature, a lot of potential for small modular nuclear, but also from a lot of other energy technologies. Some lessons learned in terms of smaller technologies are easier to finance. You can have a more diverse supply chain, so it can be easier to find components. And if you don't have a supplier, it can be easier to develop the supply chain. If your technology is smaller, it's easier to introduce innovations and iterate on innovations if you're in a factory setting. And smaller technologies tend to be less susceptible to cost overruns, schedule overruns, and labor disruptions and other kind of disruptions. I'm going to show 2 slides. So this is this really famous chart from Flodbjerg's book, How Big Things Get Done, which is a great book if you haven't read it. But what he's showing in this chart is mean cost overrun for a bunch of different kinds of large projects. And down here at the bottom, the sort of worst offenders in terms of cost overrun is nuclear waste storage projects, Olympic Games, and nuclear power plants. And so the whole book feels like it's about nuclear, but it doesn't actually mention nuclear until the very end as sort of one of the just very typical examples of how these sorts of projects go wrong because of the complexity and the scale. And then the other end, you have a lot of other small modular energy technologies, which don't tend to have big cost overruns and schedule overruns like solar power. And something else that I found really interesting and really motivated this report in the beginning that I want to bring us back to is there were 2 really interesting studies that both came out in 2020. One by Swartz et al. In Joule and one by Wilson et al. In Nature, looking at how size of energy technologies related to learning. And so that's how cost comes down with capacity build or experience with the technology. And they looked at all sorts of different energy technologies, demand side, storage, supply, different kinds, fossil fuels, renewables. And what they both found across all energy technologies is that the smaller the unit in terms of megawatts, the faster the learning. So the faster cost came down. And Wilson in particular looked at a whole bunch of different metrics of sort of success, like diffusion rate, return on investment, and found that smaller modular technologies, what they call granular technologies, just perform better on a whole bunch of metrics. And what's interesting is they don't consider nuclear at all because they consider nuclear a lumpy technology. So large, not modular, stick built. And so that's why I wanted to look, at the potential of nuclear if it was built in a small modular fraction. Could it benefit from a lot of these other attributes of granular technologies? So where does this come down in terms of, there's a lot more literature that I'm not having time to cover right now. If you're really interested, I do go into a lot more detail in the report. So I encourage you to look at that if you want to see more of the details. But I think where we came down after reading all this is that both big and small actually can work. We do see success on both in certain places, but you have to have the right enabling conditions. So there are definitely places like South Korea or China where large reactors have been really successful and they've come down in cost and they've been built on schedule. Or Sweden, as we were just talking about before the webinar started. So what you need for success with large reactors is strong demand growth for electricity and energy. It helps to have state-owned or state-supported utilities, vendors, owners of the plant so that they can coordinate. More of a paced deployment, so some sort of comprehensive and coordinated industrial policy. Indigenizing the supply chain, developing your workforce, again, that sort of coordinated strategy around the nuclear build out. It also really helps to have a productive labor force. And I just want to note, I'm not saying a cheap labor force. You can have high wages and still have cheap nuclear if you have a very productive, highly skilled labor force. For small and micro reactors, again, we haven't really built these for nuclear, but learning from other energy technology is what we think we would need for success. Would be high volume licensing. So not one-off licenses for each power plant. Factory fabrication, obviously. A committed order book to really, that helps for large reactors too, but for small and micro reactors, having that order book really incentivizes the company to invest in the factory fabrication facilities and other facilities to build the modules. Minimal on-site construction and on-site labor. That's a big lesson from NuScale that we saw, that even if you have these small modular reactors, if you're still doing a lot of on-site construction, you can have really high costs and that can disrupt your schedule and you can still have big schedule overruns. And then minimal on-site staffing for keeping your operating expenses low as well. And then lastly, something that we looked at was the second half of the report actually looks at potential market applications for these different size classes. And what we find is that there's likely enough of a market for each size class of reactor, but they really don't need to compete at all because the markets are big enough for each size. So it's more about matching the reactors to the customer's needs, or what we call right sizing reactors for markets. So just for example, microreactors, as my PhD research looked at, good for off-grid and microgrid applications, remote extractive industries like mining, defense installations, SMRs, of course, data centers are really big right now, but also industrial process heat, granular addition, so adding little bits of power to an existing grid or power plant, medium-sized grids, or even traditional utility markets if the cost comes down enough. Medium reactors, which say 300 to 1,000 megawatts. Municipal utilities, often that's a much better size match for their grids and their balance sheets. And also thermal power plant repowering, like coal plants and natural gas plants, tend to be more in that size range, and so it's a better match for replacing them. And then large reactors, there still is a big market for these large reactors, even the really big ones, particularly emerging economies that have strong growth in demand for electricity, and also retiring nuclear plants, especially if they're on the larger side. You might want to replace them with something that's kind of matching capacity or even a little larger to take advantage of the power lines and the water rights if you have them. Yeah, so that's a summary of the report really quick, and I'll go to the panel.
Thank you, Jessica. And I have to admit that I had never really thought about Olympics and nuclear storage cost overruns as being somewhat comparable. So, very interesting and very timely. We do appreciate your leadership in developing this new NIA information resource. Now, we're going to hear from some of the industry leaders who have expertise on this question of right sizing and really based on what their companies are doing right now to create the next generation of nuclear power. We're going to start with Rob Stewart, the Chief Technology Officer for Alva Energy. Rob will be followed by Rita Baranwal, the Chief Nuclear Officer for Radiant Energy. And Rita will be followed by Per Peterson, the Chief Nuclear Officer for Kairos Power, and also a professor at UC Berkeley in their Department of Nuclear Engineering. I'm not going to interrupt the conversation to introduce each person again. So they're just going to speak in the order I just listed. We'll start with Rob. Rob will turn things over to Rita, and Rita will pass the mic to Per. I'll come back after that, and we'll get the Q&A started with a directed question for each panelist, and then we'll open up the discussion with all of you. And as a reminder, if you do have questions, you're welcome to put them in the Q&A box now, along with your name and affiliation. But now, over to you, Rob.
Thank you so much, Ben, and thank you, Jessica, for a great report. As I was reflecting on it and rereading it this morning, I just reminded me that this is a very timely topic, I think, to the global nuclear industry, and so well timed in its publication. I think you have, off-takers, you have customers, you have policymakers all thinking about this exact trade-off and trying to decide what is the policy mechanism? What is the purchase decision? What is the team building, long-term planning we need to be doing? And they're weighing these exact things. This is like very timely in its contribution to many stakeholders in the industry. And I think it captures the report captures the early days reality that we're in for the small modular and advanced reactor set here, where we have a known historical deployment of the large reactor set, and we're exploring opportunities for what the future can be in the microreactor and small modular reactor space. And so, I commend the NIA team for what they put together here. I'll introduce myself a bit and give some of my background. So I have a PhD in nuclear economics, so did research in cost and construction risk for large and small nuclear construction projects. Several publications on this topic of small versus large, less in the microreactor space, but a substantial amount in the small and large. Several publications on learning rates, and I think that's an interesting thing that the report raises here is what were historical learning rates? How do we achieve positive learning rates? How do we avoid the negative learning rates of the past? And I think Jessica and I have cited each other quite a bit academically, and so this is great to get to kind of champion the work that they've done here. In thinking about the report, I think that where Jessica ended there, which is that there are opportunities at each scale, we see strongly reflected in the commercial investments happening across the industry, right? So we have private capital flowing into each one of these buckets, right? The substantial microreactor investment, there's substantial SMR investment, and there's substantial large reactor investment, both domestically and in the US. And from my perspective, even given that, the historical picture seems somewhat clear, although it's not always great news, that large reactors in theory can be cheaper, as Jessica said, and all else equal, but all else is not equal, and achieving the ideal of that cheaper large reactor is challenging and becomes difficult. And I think that I would agree with that opens the door to this opportunity for faster or just different learning rates for the smaller reactors, the SMRs, the microreactors. But I would again agree with their sentiment in the report that the magnitude and direction of these is unknown because we're early days in this space, and it's an exciting thing we're going to get to watch over the next several years as these projects deploy. And the last thing I'll note here is I think it raises the very interesting question for nuclear, which is what is learning? Physically, what is the thing that's happening here when we're reducing costs by learning by doing? And I'll give maybe 3 examples that I think are interesting, and then I'll pass it on, pass the mic. But the first is technology insertion. So you develop some new metal, some new material that helps your reactor perform better. This is research, invention, development, deployment, manufacturing that is making your product better. This is how we typically avoid learning rates in that granular size. This is solar module improvements. This is gas turbine material metallurgical improvements. This is for the sort of the highly modular energy generation products that we talked about today. This is one of the primary ways we see costs come down, technology insertion. The next one I see, and this is common in nuclear, is a methods improvement. So in the boiling water reactor fleet, you have, GE has improved their methods of analyzing these reactors substantially over the last 40 years. And as a result, the average boiling water reactor today is producing, 15 to 20% more power than when it was first commissioned. So we have learned how to operate these things better. We have developed better methods. And the same reactor that had, $1,000 per kilowatt cost or whatever it was 45 years ago, now in hindsight would only be $800 a kilowatt because we've been able to improve the power output of that reactor. And then the last one is management improvement. And this is, I think that a great example, the two great examples we see in the US fleet here are St. Lucie and the Florida Power and Light Project, and Palo Verde, the Arizona Public Service Project. So at St. Lucie, you have St. Lucie 2, the fastest and cheapest nuclear large build in the country, in the US history. 4 years, 2 labor strikes, a large hurricane, 3 Mile Island accident, all happened during the construction of St. Lucie 2, and it was still the fastest and cheapest nuclear build in the US. And a lot of that is because it was St. Lucie 2. And FPL sat down after St. Lucie 1. They didn't do anything for 4 years, but build a 1 to 200 person team to evolve, learn, think, prepare, plan, and then move forward with St. Lucie 2 at the time that they were ready to go execute the project. And you observe a similar thing at Palo Verde, where Palo Verde 3, one of the other cheapest builds and fastest builds in US nuclear history, and it was Palo Verde 1, 2, 3. By the time they got to the third one, the management team, the execution capacity, the contracts management, the procurement capability of the team had learned and was therefore great at deploying that next project. And so that is an interesting thing, I think, as we look at those learning scales, look at those learning curves, how do those apply differently or similarly to the reactors in each of these different buckets, the micro, small, and large reactors. So I think that this is a great report. And with that, I'll pass it on to Rita.
Great. Thank you, Rob. I am going to share a little bit about Radiant and what we are doing and how it actually demonstrates very nicely what Jessica and NIA have documented in this report. So give me a moment to share my slides here. Okay. Well, you saw my end, so there we go. Let me see if I can. All right. All right, can you see that? All right, very good.
Yes,
so a little
indeed.
bit about Radiant. We are a microreactor company that is solely focused on deploying mass-produced nuclear microreactors. And we are at the moment comprised of over 140 employees. We were founded by a former SpaceX engineer who reported straight to Elon Musk. So the fabric of the culture at Radiant is actually founded by the culture that it was and is at SpaceX. We also have several employees that have had careers at naval reactors as well as the U.S. National Labs. We are substantially funded in private capital. So you'll see there $525 million in private capital. That is not to say we do not need the support of the government. We absolutely do. And we do have additional capital in contracts from the government. I'm really happy to report that we have just recently doubled the size of our headquarters facility in El Segundo, California. And we also just recently announced a factory that we are going to open up in Oak Ridge, Tennessee, to manufacture our reactors and fuel them as well. So folks often ask, okay, well, yeah, that's nice. Are you a PowerPoint reactor? And while yes, indeed, I'm giving you a PowerPoint presentation here, you'll see in the next couple slides here that we are much more than that. We were competitively selected to be the first company to demonstrate our technology in INL's dome test bed. And so we're still currently on track to go critical before July 4th. So we are very much looking forward to that. We also are the first to have executed a high assay, low enriched uranium fuel contract with the US Department of Energy, as well as executing the first ever commercial HALEU contract, and that's with Urenco. We also have the first ever agreements with the US Air Force to deliver 4 nuclear microreactors to them, as well as additional reactors with commercial customers. So when the report talks about the order book that really is necessary for this industry to move forward, Radiant is absolutely walking the walk. We do have that order book. So I want to see if I can get, sorry about this, if I can get this into slideshow mode. I'm not sure if I can. There we go. So we are a microreactor company, and I like to call this a megawatt in a box. It fits inside a standard shipping container. It is 1 megawatt electric, 1.9 thermal, megawatts thermal. We are utilizing helium as the coolant and TRISO fuel particles with HALEU. As I mentioned, we have a HALEU contract. We're using HALEU in the form of TRISO particles. So you'll see kind of a cutaway of what is inside the box here. In addition to the core itself, we have the appropriate amount of shielding, and then what we call the TAC, the turbine alternator compressor, and then the heat rejection system, the heat sinks at the end. So when we are in dome, well, let me get to that in a second. So you'll see here 4 of these Kaleidos units as a depiction here. That area inside the fence line is about the size of a tennis court. And so it's really demonstrating the small footprint that you need to deploy these reactors. Our concept, once the site is ready to accept one of these reactors, it takes less than 2 days to install. Because it is helium cooled, there's really no risk to the customer site. If one chooses to load follow, they can do so. Now, as somebody who has spent nearly 3 decades in the nuclear industry, I don't know why you would take this very valuable asset and want to load follow with it, but should one choose to do that, it is absolutely capable of doing so. Here's a couple more facets about the reactor. The reactor itself is designed for a 20-year life and can be left on its own and running for 5 years. And so we refuel it every 5 years. We bring it back to the factory in Oak Ridge, refuel it, and send it back to the client. And it can be refueled 3 times. So 20-year life with three refuelings in between. And the reactor can ship from our factory by land, sea, or air. So you'll see here a bit of a timeline to the first reactor delivery. I'm not going to go over this, but we were founded in 2020 and have completed many different technical demonstrations, as well as funding raises that are very important to ensure that we continue down this path to demonstrate in dome. So what I want to share with you on our dome test is that we are testing exactly what we intend to commercialize, except for the fact that the heat rejection system cannot fit inside dome. So it will have to go outside of the dome just because of the footprint constraint by the original EBR2 dome. And so we will not be generating electricity. We will be running at full power for 150 hours. And then that heat will just be rejected to that heat rejection system. So we are for this dome test following our DOE authorization timeline. So when Jessica and the NIA report talks about needing to streamline and accelerate the regulatory frameworks. There's two things I want to talk about. The first is the DOE authorization timeline, and you'll see the milestones down below in the black piece there. But we are using not only this accelerated timeline from DOE, but we're also ensuring that we communicate the successes that we're having with DOE to NRC. And we are also pursuing an NRC licensing pathway, not only for the factory, but as well for the technology. So we're doing both activities in parallel. Now, we did invite the NRC to sit in on our preliminary design review last fall. Even despite the federal government being shut down, we were privileged to have two NRC folks in the room with us, and then 4 on the phone with us during this multi-day design review. So in the spirit of making sure that we're not being redundant as we move forward in these in the different regulatory timelines, I'm really grateful and appreciative to see NRC and DOE in the same room, hopefully behind closed doors, comparing notes as we move forward on each regulatory timeline. So what you'll see here, this was our passive cool down test that we conducted in El Segundo in September of 24. And on the right, you'll see 37 different monoliths that are all instrumented with thermocouples to simulate fuel. So we did that test successfully in 24. So this is actually our design review team. You've got folks from Radiant. We have folks from Idaho National Lab. We actually had independent reviewer, Professor Emeritus Cord Smith from MIT. And then I think the NRC reviewers are not pictured here, but they were there that day as well. The shiny foil wrapped contraption in the back of this picture is actually our heat rejection system being tested in the parking lot of our El Segundo facility as well. So all of this testing is going on to get us prepped for Dome. Getting back to the report, economies of volume is what Radiant is subscribing to. And so to do that, you need to be mass producing these. So in the fall of last year, we announced where we will be constructing our factory. It's called R50 for Radiant 50, because we're going to be fabricating 50 reactors a year. And it is going to be located in Oak Ridge, Tennessee, at the former Manhattan Project site. So we intend to break ground next month. We are hiring for up to 175 jobs at the peak production. So when we talk about, nuclear and the industry spurring economic development, while we are a microreactor company and not on the gigawatt scale of things, we are still definitely making major contributions to the local economy. We are prepared to deliver these reactors commercially. We're targeting towards the end of 27, but in print, I will tell you 2028. I'm proud to be part of a team of obsessed builders that are working towards this mission to deliver the world's first mass-produced reactors. And I will leave you with, we are absolutely hiring. So workforce development is something that is absolutely crucial to what Jessica and the report talks about. And so I'd be remiss if I didn't talk about the fact that it is very important what Pear is doing at Berkeley, what my colleagues are doing in academia, and even just out of high school, right? The folks that are going into trade schools and onwards, all of them are absolutely vital for the nuclear industry to deliver on its mission. So thank you very much. I look forward to our questions. Hand it over to Pear.
Oh, thank you, Rita. This has been fantastic discussion, and I'll add just a few more thoughts as well. A lot of what we're building on really emerged in the 1990s with work to develop passive safety systems, initially for light water reactors like AP1000, ESBWR. And we then saw a set of designs coming out for smaller light water reactors like NuScale. The transition to passive safety I view as being one of the most important enabling technology steps. The next set of things that become really interesting then do involve the question of transitioning from water as a coolant for reactors to coolants that can enable reactors to operate at higher temperature. and also to eliminate the need for high pressure, low leakage containment structures, which are required for water cooled reactors. The water has wonderful attributes as a reactor coolant. It also has a big downside. It literally can boil away. And so the safety systems that are needed to manage that do include high pressure, low leakage containment structures that do increase the cost of reactors. So when we look at the question of scaling for high temperature reactors, these reactors, because they generally operate with higher temperature capable fuels such as TRISO, they do not require high pressure, low leakage containment, which creates dramatic simplifications and very different scale economies. So what you're seeing in this space is the development of advanced reactors such as the Kairos pebble bed molten salt cooled reactor that are generally going to be smaller because as the report points out, this is where innovation is possible. And then what we can expect to see is scale up as well, both in terms of numbers that are deployed and in terms of the power output from the individual reactors. This is actually a really exciting time. And I'm going to note that Kairos is in the process of building our first reactor, which is the smallest you could make. That's Hermes. It will be followed by Hermes 2, which will produce 50 megawatts of electric power, and then be scaled up from there in order to deliver power for Google, ultimately 500 megawatts by 2035. And with that, I'll go ahead and pause and look forward to answering questions.
Well, thank you, Rob, Rita, and Per, very much. Your real-world insights on this question are really invaluable, as you have just demonstrated to us. So we're ready for Q&A, and we already have some Q&As, questions in the Q&A box. To kick us off, I'm going to ask a couple questions just to come back to some of the key points that each of our speakers made in their remarks and make sure we underline and circle them, etc. If you are adding a question to the Q&A box, I'll do my best to do them in the order we got them. Please do remember to include your name and affiliation as well. So we're going to start with a question for Per. What are lessons we can learn from SpaceX on modularity and starting small? And I'm wondering how that shaped the strategy at Kairos.
Well, indeed, and of course, as Rita pointed out, there's a number of lessons that one would want to take from SpaceX because they've been so dramatically successful. And I do think that there's significant analogies between the rocket engines that are used by SpaceX and the reactors that we're working to develop. Now, rocket engines, of course, operate for shorter periods of time. But one of the really impressive things that SpaceX has done is to make their rockets reusable. So in fact, their rockets and their engines operate for decade-long timescales. And therefore, there's a set of analogies that we can take. I think the most important is that the initial rocket engine that SpaceX developed was the Merlin, and they demonstrated it with a single engine on basically the biggest engine that you could have with a single rocket that could get into orbit. And then after being successful with that demonstration, they then moved to an architecture of 9 engines on a rocket. And what they were doing was leveraging two things that are similar to what we are doing with small modular reactors in multi-unit configurations. One is there are significant benefits for reliability of having multiple engines. And in fact, the Falcon 9 can have a single engine fail and still make it to orbit. Those benefits in terms of reliability will also be important for deployments to support loads such as data centers. And so I think there's going to be a set of use cases where multi-module installations are going to be valuable. The other thing with rocket engines is that the various pathways to upgrading the power output, and Rob had mentioned this as well, the thrust of these engines has gone up dramatically by a factor of a few over the development cycle. And we should expect to say the same thing, because the more energy or the more power you can get out of a reactor of a given size, the more revenue that it can generate. And so the combination of modularity, power upgrades, and then the final thing to point out is that the transition to the Raptor engine, which is much larger than the Merlin, but builds extensively on the experience and makes some major architectural changes, is now what is enabling Starship. And Starship has got 33 of these. So it is definitely a multi-module ship with really big rockets, which makes it, of course, the largest rocket ever developed. The strategy there ultimately is to drive down the cost of launch to be far lower than ever, historically. And the goal for reactors, I think, is the same. The combination of modularity, scaling up, and power, recognizing that there are scale economies, but the ability to build reactors in large numbers is what's most important to drive down cost. The goal is to drive down the cost of power production and of energy so that in the future, energy becomes abundant, affordable, and clean. And that's the real potential that we're going to see with nuclear power. And I think this report really provides important insights about how we're going to achieve that.
Well, thank you, Per. So far we've touched on the Olympics and SpaceX. I'm looking forward to what the next business or economics comparison is. I don't know what it'll be, but I can't wait. Let's go to Rita, and just to give you a chance to go back to the excellent presentation you gave us and hone in on how the size of your reactor shape, or the size of your reactor, how it shapes how you think about innovation, because clearly innovation is a big thread in what you're doing. You talked about it a lot. So the size piece, how does that sort of shape how you look at the innovation question and how you're tackling some of this?
So I think the size piece certainly works to our advantage. If you're, I want to talk about two things: one, technical innovation, and then process and regulatory innovation. So the technology side of things, it allows us to be more nimble as we're testing the components of the reactor itself, as we're starting to put the systems together. You don't have, of course, I mean, the big bulk that you would have in a gigawatt scale reactor. So certainly allows us to be more nimble and iterative and design, build, test in that do loop that I know that Kairos and others also follow. And there's a lot that Radiant does in-house that makes it just so exciting as a company to watch and see how all of our progress is moving forward in this iterative design, build, test process. We do pull in experts as we need it, and we pivot as we get that data in. So I think the size is certainly to our benefit as we move forward. The size also helps us in terms of regulatory and process innovation. So the reason I joined Radiant was because how forward-thinking the leadership was and how willing the company is to be a fast mover and to take calculated risks. And to have the kind of the difficult conversations that start with, why did we always do it this way? Why do we still do it this way? And why can't we do it this other way that is more efficient? It might be faster, but it still provides the same end result. And that might be the safety and health of the public. It might be that you go critical at a certain point, or there might be, there's a slew of other end goals that these regulations are designed around. So it's really exciting to be in this space at this moment, given the positive attention that nuclear energy has worldwide, the tremendous support that nuclear energy has from the administration in the United States, and then the financial support that the industry is getting, not only from the government, of course, actually it's globally, right, from governments globally, but also from the private investors that I've talked about earlier in my presentation. So we've got a lot of things going for us. We need to continue to move forward, move carefully, of course, but move forward with a huge sense of urgency.
Thank you, Rita. And let's go to the other end of the size spectrum. Rob, you talked about this a little bit, but go into a little bit more. What would be needed for large reactors to be successfully, and I guess I mean cheaply, built in the US? And what are the enabling conditions, to steal from Jessica's slide, for that success from your perspective?
Yeah, this is a great question. And I respectfully asked for 15 minutes to answer this question, so I'll take the rest of the time of the call here to provide an answer. Thank you, everyone, for allotting me that. No, jokes aside. So I think that this is a great question. So for utility scale deployment in the US, to deliver on the 200 gigawatts that the US Department of Energy wants in new nuclear, to meet the emerging economy need, like large scale nuclear gigawatt size plants are going to be a required part of the deployment portfolio that we need. And so answering this question actually is the central thesis of what we're building at Alva. I have not talked much about Alva Energy. That is the company I'm the chief technology officer of. And we've spent several years researching this question and then building the team to execute against a particular vision as we try to answer it. The first thing I like to point out is that at the same time, a lot of builds were going terrible. At the same time, Washington Nuclear Power Project 3 was driving the largest municipal bond default in the country's history until Detroit went bankrupt in the financial crisis of 2008. That same reactor technology at that plant was being built as the fastest and cheapest build at St. Lucie 2. And so what was the difference there? Why did the same reactor technology equal the fastest and cheapest project and the largest municipal bond default in the country's history? Why did Palo Verde 3 get built so fast? One of the advisors to our, two important advisors to our company on answering this question is Bill Derrickson, who built St. Lucie 2, and Sven-Erik Rosen, who built Forsmark 3, one of the fastest builds in Sweden, coming in around 6 years. And it's very interesting to me to look at the same time you had these projects going enormously well and some going absolutely terribly. And drawing the line and what's happening there is a lot of it comes down to the project management and execution capability of the team. What we observe over and over again in looking at the utilities is that, and you can read it in their Public Utility Commission reports, or sometimes the PUC is hiring an external consulting firm to review the performance of the utilities management team of Louisiana Power and Light, of Washington Nuclear Power Project, et cetera. And what you see is that they were only going to build one reactor. They needed 1 gigawatt power reactor to deploy in their municipal area, and they weren't going to build another one. And so investing in the capacity to execute the projects well was often an area that was underinvested in. And where, in contrast, you see Bill Derrickson at St. Lucie 2 investing enormous amounts of time and engineering resources, not in the engineering of the reactor itself, but in the engineering of the project to deliver it at a particular time and scale. And we observe this in the companies that do some of the largest capital deployments annually in the country. You have ExxonMobil, who does tens of billions of dollars in capital projects every year, and they have a whole organization devoted to global project delivery. They build up train expertise. They build that. This is something that is built into the DNA of this organization. And there are particular skill sets here that are required to deploy these projects well. There's risks that have to be thought through in contracts and structures and supply chain. I could go on and on and on, but where I will limit the rest of my answer to is I think that the Vogtle experience gets kind of thrown out as an example of poor execution. Large reactors cannot be built fast. And Vogtle, for those who don't know, was 2 US AP1000, Westinghouse AP1000s. They were built around the same time that 4 AP1000s were built in China. And I think that there's this common sense in some circles that things built in the US cannot be built at the pace that they can be built in China. We see China build an entire country's worth of high-speed rail in the time that we have deployed, maybe half a mile of high-speed rail in California. We see lots of demonstrations of a deployment capacity in countries outside the US, and we wonder, why can't we do this here? But interestingly enough, those 4 AP1000s in China averaged 8.5 years of construction time, and in the US, it was 9.5 years. In hindsight, we were actually not that far behind as a country in our ability to deploy large reactors compared to China. And I think that the myth I'm trying to dispel here is that there's this idea that large things cannot be executed well. And we just completely disagree with that idea. These things can be managed, they can be executed well. And what we observe now is in the next wave of AP1000s, where they've domesticated a lot of the supply chain to reduce the supply chain delay risk that plagued the first round of projects, China is now bringing on their domestic AP1000 technology in less than 56 months. So that's less than 5 years of total nuclear construction. That would be faster than any deployment project for any commercial reactor in the country here, if we could do that. And I think that this is an important way to look at these projects, is that as you de-risk your supply chain, as you do proper engineering and project planning, these projects can be done well and executed cleanly.
Well, you didn't need 15 minutes, but I think if you had taken it, it would have been fascinating. So thank you for that. We're going to get to questions in the Q&A box now, and we have a lot of them. I don't think we'll get through all of them, but we will see what we can do. First one is from Doug Vine at C2ES. Hi, Doug. Have you also evaluated the complexity of designs and rarity of materials? Fewer parts versus more parts, and the exoticness of the materials versus designs that use more common materials that are being used across the different sizes of reactors. Do these factors make a big impact on the economic viability? So I think the question's to Jessica in terms of the broader literature review, but maybe if one of our company folks wants to answer?
I can give some insights in this question. As you go to new reactor technologies, they will use different materials and fuel types, things such as higher enrichment levels for HALEU. What's in the back of my mind is two questions. One of them is, how much is there? That is, would we be constrained to scale to very large power levels by resources that are available? And in general, when we look at the high temperature reactor technologies like the FHRs, the answer is no, there's more than enough natural resource. The other question is, how rapidly can you scale manufacturing? And one of the neat things about the smaller reactors is that in general, doubling the number of units that you would manufacture can be accomplished pretty rapidly. So once you've got the correct technology and design, the ability to scale to much larger deployments, I think, also exists with the various different high temperature reactors that are being described here today. The big question is, when you scale them to be large, how do they compete with large light water reactors? And there, I think that we see real potential for some of the systems, such as with molten salts, to come in at substantially lower cost than large light water reactors when scaled to those sizes. In part because you'll eliminate the need for these high pressure, low leakage containment structures. But this is something I think it's a really important question. That's how I would answer it.
Thank you, Per. Anyone else want to jump in before we go to one of our other questions? Okay, so this is a long one.
I think Jessica went off mute. Sorry.
I was just going to add quickly, I think the literature has a lot of examples where new designs have had some trouble with novel components or novel materials that have slowed down processes. So it is something to really make sure you understand the supply chain before and take the time to figure that out beforehand. So it can have advantages, but it can also be a challenge.
Thank you, Jessica. And leave your mic on because this one's for you. You indicated you would answer it live. It's from Niels Harksen, German Nuclear Advocacy Group, and he's also a mathematics student in Berlin, Germany. So we have covered the world here. A lot of empirical analysis finding negative learning in nuclear or problems with very large reactors suffers from one issue. The last and usually largest reactors being built in Europe, US, Korea were constructed under much more challenging political and regulatory conditions than earlier reactors or in much smaller numbers. Therefore, any favorable effects of learning based on total installed nuclear capacity or upsizing single reactors are overshadowed by far more powerful effects. Especially anti-nuclear empirical research has used this to claim that nuclear has unexplainable negative learning rates. So the question, is this dynamic something you consider and try to compensate for / filter out in your analysis?
So I will try to answer this quickly. This is obviously my area of expertise. I've written a lot on nuclear economics and the historical data, but I will say I think regulation gets blamed a lot for the negative learning. I think it's a misconception and a misuse of that. We, especially NIA have done a lot of work on the need for regulatory reform, especially in the US with the Nuclear Regulatory Commission. I think that's going to be very important to make regulation more streamlined and efficient, especially for these new advanced reactors and non-light water reactors, and smaller reactors and high volume licensing, and that's going to be very important. But for the reactors we built in the past, increased regulation did not have a big impact on the cost and the timelines. There were many other factors that went into it, including project management. As Rob said, you had reactors being built super fast at the same time as reactors being built super slow and way over budget. So in the same regulatory environment. So there's something else going on. And you can see this in a lot of countries. So I'd be happy to talk more if you want. We can schedule something offline. But I have a lot to say on it, so I'll keep it short.
Thank you very much. We'll have time for one more question. It's from Christopher Forsyth, an MIT PhD student. Thanks for the great panel. The report mentions that industrial applications and data centers may be the right use case for SMRs, but does not appear to consider the economics of competing technologies for these applications, such as enhanced geothermal or gas with carbon capture. Most non-nuclear technologies have weaker economies of scale due to lower fixed costs, making them more scalable to small applications. How does this affect the competitiveness of SMRs? Interesting question. Anyone want to jump on that one? Looking around the room. Anybody? Jessica, do you want to go back to the report?
I think different companies are, I think Chris knows this, but different companies and different designs are tailored to industrial processes. So not every SMR is going to be a good fit for industrial processes. And it has to do more with how much heat you're producing and the quality of the heat and the quality of the steam if you're producing steam. So I think it's not any SMR is going to be a good fit for industrial applications or any size, but certain companies who are targeting industrial applications are optimizing for that. And also because nuclear does have a lot of excess heat, it can be a good fit for industrial applications compared to other technologies that maybe don't have that excess heat. But we don't know. Maybe it won't be competitive in comparison. And maybe that's why a lot of nuclear companies are pivoting towards data centers or other applications.
Thank you. Anyone else want a final word before we wrap up for today?
Perhaps just a quick note. All of these different technologies have potentially significant siting constraints, geothermal in terms of the geologic conditions, carbon sequestration as well. One of the interesting points about small modular reactors, particularly those that fall in the low hazard category, is the likelihood of dramatically simplified siting because of the ability to have a site boundary EPZ. And so this may end up being one of the major competitive advantages also for multi-unit small modular reactors co-located with various types of energy loads, including data centers.
Thank you, Per. And, I think it's really clear that we have only scratched the surface. We could talk for another hour at least. Unfortunately, we don't have time. So if we didn't get to your question, and there are several of you that we missed, we will follow up by email. So be on the lookout for that. And with that, our rapid hour has come to a close. I hope this conversation has helped you consider how we can best right-size reactors, and I invite you to download the report from the NIA website. Again, the main URL is www.nuclearinnovationalliance.org. You should also join the more than 4,200 people who follow the NIA on LinkedIn. All kinds of great timely updates on their work and perspective on news of the day there. But for now, please join me in thanking our special guests, Rob Stewart, Rita Baranwal, and Per Peterson for joining us today. On behalf of Judy Greenwald, Dr. Jessica Lovering, and the entire NIA team, thank you for your interest in advanced nuclear reactor technologies, and thank you for joining us today. We look forward to seeing you online again very soon for our next webinar, and watch your email for those invitations. And have a great day, and happy January.